Hello, and we're back with a brief overview of what we covered last week. Well, depending on when you're viewing this, I suppose that might not make much sense, but a brief recap of what we talked about in the last few mini lectures. Displacement and position, velocity, at least the average form shown here, though we talked more generally about velocity, and acceleration. All right. And right at the end of the acceleration lecture, we started talking about a situation where we were assuming that we had a constant acceleration. And that might seem quite limiting, but one, it is a nice example because it simplifies a lot of things, and two, it's actually a condition that either we are in or we are close to being in a whole variety of physics problems. One of the primary ones, which we'll see an example of in a future mini lecture, is an object in free fall, where the acceleration due to the gravity of the Earth on an object is, near as makes no difference, constant for objects falling near the surface of the Earth. So, and what we saw there is that if you have an acceleration that does not change as time goes by, then that means that the slope of a v versus t graph must be constant. And since we have a positive constant acceleration in this example, that means a positive constant slope for our v versus t graph. And that in turn means that we have a linearly increasing slope for an x, so a position versus time graph like we have down here. So we start with low slopes down here, and we move to higher and higher and higher slopes as we go along this parabolic curve. So, with these definitions of acceleration and velocity and displacement, plus the assumption that we have an object that is moving with a constant acceleration, we can write down equations of motion that connect all of the different quantities that we've been talking about thus far, time and velocity and acceleration and displacement and position, all of these things to one another. And all of these equations are self-consistent. In other words, they all sort of point at one another. If you're using acceleration in one, you can just as well use that acceleration in another, and you can solve for any one of the things if you know enough of the other things. There's no special cases here other than assuming that acceleration is constant. Okay? Now what I'd like to talk about primarily in this mini lecture is how on earth we get the form of these things. Some of them, if you stare at them just a little bit right now, like this one, okay, might look tantalizingly close to just some of the definitions that we had on the last slide. But a couple of the others might look a little more esoteric, and we're going to step through the basic algebra of figuring out how these things must be the case. And for those of you in my Physics 200 class, engineering physics, we'll go a little more in depth in a future mini lecture as well to show how these are related to the calculus definitions of and relationships between position, displacement, velocity, and acceleration. Okay, so let's jump right into it. Here's our four equations of motion that I had across the top of the slide on the last slide. And here, again, as a reminder, is a graph of constant acceleration, not changing over time, in this case, some positive value that is maintained for as long as we are considering the motion of an object. Okay, so first let's look at this equation of motion across the top. And the way that we get that is by examining the definition of acceleration. Okay? If we look at the definition of acceleration, one, I dropped the little bar here because if you have a constant acceleration, well then that's the instantaneous and the average accelerations are all going to be the same number, right? If you look at here, or here, or here, and here, and you average all those together, you're going to have the same value whether you're looking at the average or whether you're looking at any one of those values. Anyway, so that's delta V over delta T, and I've written out what that means here. And if we just do a little bit of algebraic manipulation, right, we can get an equation that looks like this. And if we squint just a little bit, we can see that that is exactly the same as this equation. What's the only difference? Well, the only difference is that, one, I would have to add v0 to both sides, right? That makes it look a little bit more like what we've got up there on the top line. And the other thing is to assume that our initial time is equal to 0, right? And that's safe. We can start our stopwatch for a particular calculation wherever we like and let it run to whatever final time. So if we just simply rewrite that and reorder this side and call time final just t, then there it is. Okay, and I've written that algebra out in, sorry, went the wrong way, in slightly different form here. Okay, just to show the algebra in neater than my handwriting form. Okay, so that's the first one taken care of, and that comes just from the definition of acceleration and the assumption of constant acceleration. That's it, okay? And the others are going to follow along in much the same way. We're skipping down a little bit. We're going to check out the fourth one on the list here at the moment. And remember that our corresponding graph of velocity versus time for an object is something that has, right, for a positive acceleration, a positive slope. And I've picked an example here where we don't start at initial velocity equal to 0. It's some value, but we leave it indeterminate. And after some time t has passed, it has accelerated to the point where it's at some higher final velocity. Now, because this is a line, because we have constant acceleration, not some varying acceleration, well then, the average velocity of the object during this time must be exactly the midpoint between these two values, okay? Final velocity and initial velocity. Must be exactly the midpoint. You can kind of hand wave your way to that by realizing, well, that for every point above that dotted line representing average velocity, there's a corresponding data point equal distance below it. Equal parts of the line are above and below that average velocity. If you had a varying acceleration in some way, well then this wouldn't necessarily be the case because the slope of your velocity graph would be all over the place, right? It wouldn't be a straight line. But here we can say that, as we know from calculating averages, that the average velocity is simply 1/2 times the sum of the initial velocity and the final velocity. Okay, that's supposed to be 0. Okay, so that you can kind of pull from the graph, and I hope my argument made some sense to you. And then from that point, the only extra step that we need to take to get to this fourth equation of motion in my list over there on the left is to recognize what the definition of average velocity is. What's the definition of average velocity? Well, I will tell you, and you should remember. It is delta x over delta t, okay? So when we make that substitution and do a little bit of algebra, we can get to that fourth equation of motion that we're seeing over here, okay? So I will lay out in terms of the actual printed slides. Maybe I'll post these on the Brightspace page along with these mini lectures at some point. And then we also have this, so that and that, okay, which I mentioned on the last slide. And then we can simply substitute one into the other. So bring this down, and we have delta x equal to 1/2 vf plus v0 times delta t. And the only thing we need to do here is, again, assume that t0 equals 0. And that way we can just write it exactly as we have it over there on the left of the page. Okay? So I'll put that in print, but that's where we get that fourth equation of motion in our list. Just from, again, constant acceleration implies this, and all of the arguments I made about what the average velocity has to be in relation to the initial and final velocities, and then we just applied the definition of average velocity, and off we go again. So there it is. Now, for the other two, really all we need to do is some simple algebra, okay? Because at this point, we can sort of substitute one of the equations of motion that we have already into the other, as I'm implying with this little arrow here, and rearrange it a little bit, and we'll get to the third equation of motion in the list. Let's check it out. So if we substitute final velocity, so we'll write in this for that, well, then we get an expression that looks like this. Sorry for my writing. Okay, so we have two factors of initial velocity, and we have acceleration times time for the third thing in the sum here inside the parentheses. And if we distribute that t on the outside that we carried down from here, well, then we get the following. So we get the two factors of v0, that cancels the 1/2 that's sitting out in front of the parentheses. So on this term, we just get v0 times the t that we distributed in. And for the second term, well, the half doesn't get canceled. We get at squared, because when we distribute the t, we get two factors of t. And that, right, is just this equation of motion. So I'll show you that there in better script. And lastly, we can get the second one in the list of equations of motion by making another clever substitution, essentially just eliminating a different variable. You'll notice that that equation of motion right there is the only one that doesn't have time in it. So if we take this equation of motion and we solve for time, well, what we get is something that looks like this, okay? And if we take that and we substitute it in to that same equation of motion that we started with before, right, the fourth one in the list, if we substitute for time instead, well, then we get this thing. So I'm going to pull the a out there, and then we get the sum of these two things from our average times the difference of those two things from this substitution, and we multiply that whole thing by time. And this looks kind of nasty, but it actually simplifies really well, because you'll notice that all the cross terms, when you do the FOIL method on this thing here, all the cross terms just disappear, okay? And when you do that, what you get is exactly what we've got, well, almost exactly what we've got in that second line of the equations of motion. There's a couple of steps in there, right? When we do this whole thing, you get the v final squared, you get negative v0 squared, and when you do that, I'm sorry, this is substituted for, okay? And when you do that, you get something that looks like this. And all you really need to do is multiply both sides by this 2a and rearrange things a little bit to get things looking exactly like that second equation of motion, okay? That's it. Now, the real power of this remains to be seen, right? We haven't done very many examples with this, though you're working on it with your assignment, and I've posted a couple little videos showing some of these equations of motion in action. But I think it's, you know, for me, when I was first starting out in physics, this was an inspiring moment to realize that the only, other than just defining what acceleration and velocity means, which really, that's a pretty basic thing, and then making this assumption of constant acceleration, that we can get this nice little concise set of equations of motion that we can then go on and apply to a huge number of objects in terms of describing their motion and predicting their motion and relating parts of their motion to other parts and all of those kind of things. That was one of my little, you know, formative moments in my physics education, and I hope you are similarly inspired once we see how these things can be applied and how widely. So with that, I think we'll leave off, and the next time we'll start with this example. Thanks for your attention.